So this lecture is about the ideal gas law, which remember, all along we've been changing four particles. We've been changing pressure, temperature, volume, and number of particles. So when you change the number of gas particles, it's going to affect the other three. So anytime you change one of those four variables, the other ones are affected. So the way that the ideal gas law is different from the previous ones is, in the previous ones, at least one or two of those four variables were kept constant. In the ideal gas law, all four are changing at once. So, for example, if you increase the number of particles, it's going to raise the pressure and volume. If the pressure and temperature are constant and more gas are added, the volume will increase. So the take-home message of the ideal gas law is now all four variables are changing. We're going to use something called the gas constant, which is the big capital R is the symbol. Remember, the word constant means always the same. So the gas constant is always the same, and it's never mentioned in the problem. There are four different values of R you can see listed here: 0.0821, 8.314, 62.4. And if you take a look and compare the units of pressure, volume, temperature, and N, you see that for volume, temperature, and N, number of moles, the units are the same. Now, one thing, if you're going to use R, the units have to be these units. You're used to using moles, you're used to using Kelvin. Here, though, the volume has to be in liters. Only for this gas law, though. The volume has to be in liters. What changes the value of R, what changes the number, is the pressure unit. So if the pressure is in atmospheres, this is the R value you use. If it's in kPa, this is the R value. If it's in mmHg, this is the R value. So one of the key concepts here is the whole idea of a real gas versus an ideal gas. Remember, the word ideal kind of means perfect. In a perfect world, this is what it should be. An ideal gas is one whose particles take up no space and have no intermolecular attractive forces. Basically, they don't affect each other at all. All the gas particles act independently and have no effect on the other particles' behavior. Again, this is an ideal condition. It probably doesn't happen in the real world. But ideally, this is how gases behave. They take up no space, they have no attractive forces, they don't affect each other at all. These are what follow the gas laws under all conditions. But of course, in the real world, no gas is truly ideal. All calculations we make with the ideal gas law are approximations, like you've seen over and over and over again this year. Just because the theoretical value should be X doesn't really mean that during an experiment you're going to get that number. We call the real world gases real gases, so it's an ideal gas versus a real gas. Real gases deviate, meaning go away from or most unlike ideal gases, at extremely high pressure and extremely low temperature. So the explanation for that is, remember that in an ideal gas, there's very little attraction, there's very little interaction or stickiness to the particles. So if you think about very high pressure, the volume is very, very low. So under very high pressure, the volume's low, they're very close to each other, so they stick together more likely because they're so close and they're going to run into each other more often. At low temperatures, they're moving very slowly. So when they hit, they're actually hitting and actually sticking for a bit. So the opposite of that, gases are most ideal when the pressure is very low and the temperature is very high. The pressure being very low means the volume is very big. There's a lot of space between the particles to move, so they actually just physically don't come in contact with each other that often because there's so much space to move around. And then high temperature means they're moving so fast that even if they do come in contact, they kind of just ping off each other and have very little effect on each other. The nature of the particles making up the gas also affects how ideally it behaves. For example, if it's polar versus nonpolar, remember, polar molecules will stick together more often than nonpolar. There are two derivative equations from the ideal gas law equation. So this is just how you derive them. This is the process, but really what you need to know is right here. If you want to use molar mass and actual mass, you use this equation. So big M stands for molar mass, little m is actual mass, RT over PV. And the one at the bottom takes advantage of density. So density equals the molar mass times P over RT. So the first sample problem, calculate the number of moles of a gas contained in a 3-liter vessel at 3 times 10 to the second Kelvin with a pressure of 1.5 atm. So again, I'm writing all my knowns down, and notice with the ideal gas law, there is no 1, 2, first, second pressure, volume, or anything. So I have my volume, my temperature, my pressure. Now notice R is never mentioned in the problem. You have to know that R has to go there. The value of R, remember, depends on the pressure. So if it's ATM, it's 0.0821. Don't really worry about the units here, and then N is what you're solving for. Also remember for R, volume has to be in liters. So once you get here, it's just a matter of plugging in and solving. Very simple. And you get N equals 0.18 moles. So these next problems are going to be the derivative problems. So you see, what is the molar mass of a pure gas that has a density of 1.4 grams per liter at STP? So in this case, STP are conditions, 1 atmosphere and 0 degrees Celsius. They're not the molar volume thing because it's not asking for molar volume. So I have a density of 1.4 grams per liter, temperatures STP, 0 degrees Celsius, 1 atmosphere, my R value because of the ATM, and we're going to look for molar mass. Now notice the density formula. You're used to seeing grams per milliliter, grams per centimeter cubed. It has to be grams per liter because the volume is in liters. If you're given a density in the problem, though, it will be given in that way. So then you just take your derivative equation. We've actually switched it up a little bit, but you can use the original one. Plug in your numbers, solve for molar mass, and we get 31.38 grams per mole. And that concludes this lecture.